I do believe we have Markus up next here to talk about open science beyond data sharing.
All right. Let's see. All right. Can you see the slide?
Yep, that looks good.
All right. So I'm really excited to be part of this workshop, and I was going to give a little bit of a PI's perspective, showing some of the work we have done, and also outlining some of the trouble or pain points we have sort of run in. We've seen definitions of open science, and there are many of them out there. I have one pulled here from the web as the practice that others can collaborate, contribute, and research data, lab notes, and other processes are freely available for reuse, redistribution, and reproduction. And I think there are really 4 pillars to that. So the first one is open access. Everyone's familiar with this by now. Then there's the open data and data availability policies. And I think everyone's on the same page there as well. But then there is also the open software side and open hardware side. And when we think about open software, I do a lot of laboratory stuff. So there's also this issue of data acquisition and processing scripts. And they should be available under a free license and a free software tool chain. And in the last 2 realms, I think there are still ways to go to actually get this up to scale. So I'm just showing 2 examples of instruments that are actually also deployed by ARM, which is a size distribution measurement, and it comes with manufacturer proprietary software that does the data acquisition, that does actually some of the inversion, and then produces a binary data file that then can maybe be exported, and then the analysis chain starts from there. And similarly, the CCN instrument depicted here comes with some closed source LabVIEW code. So the first steps of the sharing are sort of like still broken there. So I want to show sort of a few examples on stuff we have been working on. So this is a tool to do some inversion of SMPS data and tandem mobility data. And it comes with 2 repositories that are currently hosted on my GitHub site. And so if you're interested in inversion stuff, feel free to check that out. But what I wanted to talk about is more of the philosophy here. And so this is very specialized software in a way, so that is targeted to developers, quote unquote. And with that comes that it's still relatively difficult to learn or to use. There's a big challenge to document these codes. I hope I did a reasonable job there. But it's the documentation, I think, is really critical and a very time-consuming task. Another issue or challenge that I've often run in is the need to maintain these things. So from an author perspective, we tend to write papers and then we're done with it. But software must, of course, be maintained. The reason is that there's lots of dependencies in this software, and then the entire ecosystem moves, and these dependencies tend to break. It's not a huge amount of effort to maintain these, but it needs to be done for quite some time into the future. And then on the teaching side, I have made some tutorials and tried to get this out via containerization. But to make it really more usable, it needs a front end for users. I'm currently working on one, but that's yet another layer of complexity that has to be put on top of these tools. And all of that, bottom line, comes with some time commitment in the future relative to publication, and that's really something to consider. The second project I've been working on is educational related. So these are interactive worksheets for teaching about aerosols in cloud physics, and you can check out the article in BAMS. it does come with a repository on GitHub, and underneath it's really a number of Jupyter notebooks with interactive content. And the target here is it's teaching material for instructors and students. It was meant to be easily adaptable. And some of the same challenges here, I think, persist. Like this whole thing requires maintenance. It's actually not as easy to install as I would hope. And then there's the question of scalable delivery to students or workshops. And so I'm outlining in the paper how this can be obviously done with a Jupyter Hub server. And I'm currently working on sort of a more private server that does this without the need for authentication. That hopefully it is online, and it hopefully will be public soon. So the idea is that people can just access it via web link or something like this. I want to talk a little bit about open hardware and some of the challenges here. So we recently published a paper about an open hardware precipitator, and the technology itself is not so important here. The idea is that it's a low-cost instrument and something that can be manufactured by a graduate student. And it's really designed to enable participation and is supposed to work on really simple parts. Challenges again here are documentation. There's multiple repositories that are needed to make this work. And then on the maintenance side, both the software and hardware platforms can be aging, so that that requires maintenance in the future, and there is a challenge there to keep these things up to date for some time. There is one more of these things we're working on, which is an ice nucleation cold stage. So this is actually funded by NSF. And so if you're interested in doing ice nucleation measurements, the cold stage can be requested via a funding process through NSF. And so if you're interested, go to that website or send me an email and I can tell you more about it. But as part of the grant, what we're working on is also a low-cost version of the instrument, similar to the precipitator, also for self-manufacture. So all the ideas are the same, and all the challenges are similar to the previous one, with the additional question here that the manufacturing methods are a little more involved. It requires 3D printing and a few more advanced tools. So to get this well documented and really out in the useful realm of open hardware, we also need to take into account the skill of the target customer, which is early career, early stage graduate students. Now, what do we hope to achieve? Call it the virtual cycle of open science, but the hope is that there is sort of a space for instrumentation that maybe in the range of below $10,000 or even below $5,000, that as students or research groups have questions, that they can pull up a tool and build it at this moderate cost. Like a few $1,000s are relatively easy to come by. The students learn to build the instruments themselves, so they gain hand-on skills and hopefully can share design improvements. So the tagline would be better graduates, faster science, cheaper science, and improved instrumentation. But to make this work, and let me go to this first. So the idea here is that the open science has many facets. I pulled this up from a recent FOA. So what DOE is mentioning mostly is reproducibility and availability to other researchers. But in a broader sense, it also has to be useful and go to a targeted audience. So the themes for discussion really that I want to throw out is there's the incentive side. So there's the time and funding requirement and the recognition requirement. And I think DOE has done a really good job on providing that. There's some philosophical questions, I think. that are related to what we really should archive. So if you go through the entire chain from data acquisition to published product, there tends to be a lot of clutter that is produced, and so there should be some real targets on what really constitutes archivable data. Software archiving is notoriously difficult because it breaks in the future. And then there's the question for whom we generate these products when we put them out, at least from a PI perspective. And on the technology side, having played with a lot of the tooling, I still think it's relatively complex, and there's no 100% satisfactory solution to do the entire chain in a reasonable way. And I'm thinking here on containers layering on free software, and then those containers breaking. And so there are challenges, I think, that we somehow need to solve as the community. So with that, that's all I have, and I can stop sharing here.
Thank you, Markus. So we do have a comment or a question in the chat here from Shui Qi, and please correct me if I did not pronounce that right. But for the revisited SMPS and HTDMA data, are the data available for users to use, or do they have to use the tool to apply on raw data?
So the data are also available, of course, in the with the publication or in the archive. The manuscript itself was mostly about the tool, but for future data sets, it just will be applied, and then we'll say this was the tool that was used, and then both the raw data and the inverted data would be available together with the publication.
Great, thank you. Are there any other questions for Markus? I guess, well, if there are people raising their hand, you know, before they do, I'll ask. So one of the things we struggled with was, you know, the citation route for the open source, whether you do the paper, whether you do, you know, the connection from GitHub to Zenodo or something like that. You know, it looked like that was one of your challenges as well. So do you have a preferred method going forward that you like to use, or do you see the community gravitating a certain way?
So I've done both. I mean, I have it on Zenodo and I have it on GitHub. It seems to me that Zenodo goes stale more quickly. You can keep them in sync, but the issue becomes that there's too many places where there's the same thing, and then people might get confused on which one should I use, and which one is the official one, and which one is the most up-to-date one. But not having on Zenodo means it doesn't have a DOI, and then it's not really citable. And so, yeah, this is one of the what I would call non-idealities of the system. The other problem is if it's just on GitHub, it can disappear, and I find that problematic, because if I were to feel like it and I take my site down tomorrow, then the software would be gone, and that would belie what's in the paper.
Yeah, that's a good point. Okay, are there other questions out there? You know, Scott, you were commenting, but I didn't really see a question. We do have a question. Can you talk more about the atmospheric physics notebooks? Can it be freely used to teach atmospheric physics?
Yes, it can, and I can. I'll put the tentative web link in the chat in a moment. So you can use them right now. So they're distributed as a Docker container when you go to the site, and it's linked in the paper as well how to start up that Docker container. But that using a Docker container is good for single users, and mostly PIs and graduate students have no problem getting to that point. But if you want to use it in an undergraduate course, The idea is that each student will get their own containerized environment, which is usually done via a Jupyter Hub server. And that is something that needs to be set up to scale through a Kubernetes cluster. And then that costs money very quickly because you have to go through a cloud provider. So what I have been working on is to deliver these containers on a smaller scale server. It doesn't have an infinite number of connections. That's why I haven't put it up at the moment. It can handle, I think, 50 at the moment, 50 simultaneous users. And you should be able, this one, it's currently unofficial, but hopefully by the end of the summer, it will be official. Anyone in the community is allowed to use that server also for teaching purposes. So if you have a class, and I don't think anyone is teaching more than 50 students at the moment, you could just give the class that link, and for all intents and purposes, you can do that, then use that without cost. And that server is courtesy of NSF at the moment. So, but you can also, and that's described in the paper, you can always set up your own cloud environment and run it there as well.
Okay, great. Another question came in. Can you comment on how much time you spend on the infrastructure/maintenance piece versus the actual development in some of these projects?
Yeah, so I think the development time is definitely larger than the maintenance time. I think if I have been struggling a lot, I think with the packaging, and that's mostly because I'm not a trained software developer, so having to like learn containerization and putting these things in a package that's usable has taken a lot of time for me. So I don't know, a lot of it has been learning time, I think. The maintenance part is so far relatively hands-off. I mean, there are GitHub workflows that alert me that dependencies updated, or when I do everything in Julia, so when the new Julia version comes out, I usually download it and run the tests, and if they break, I fix it. And it's relatively fast, but it's sort of a continuous onslaught, I think, is the problem, and the real commitment for that this carries on many years in the future, so the projects don't become abandoned.
Thank you. One thing to note, you did mention you do a lot of, or all your development in Julia, and we didn't include a tutorial on that in this workshop now, but I am curious if there is interest from those on the call in a future tutorial on Julia. Please, put up a reaction or something, put in the chat a comment, but it would be great to know if there is interest in setting something like that up. I'll put something in the chat here, and if you want to add a reaction, go ahead. But are there any other questions? Otherwise, if there are, we can just keep it in the chat, and we can